Thanks, Sridhar, for exciting talk. Okay, so we have several questions. So let's see, how do I start with there are two in chat box. So let's start with that. Raja is first. Raja.
Thank you, sir. Hello, Sridhar sir. How do you do? This is Raja.
Yeah, hi
Seeing you
Raja.
after a long time,
Yeah,
and it's very interesting talk.
thank you.
I just have one simple question, maybe because I'm not from the field, so that's the reason asking. At page number 14, 15, you try to show about these mixing events, try to show about these Kelvin-Helmholtz instabilities or linear Hombé waves kind of instabilities, what one will see. After that, you try to calculate these production terms, production buoyancy terms, and yeah.
Yeah.
I'm just curious, what actually special about this particular Z by H? The set value from 0.25 to something like it shift towards 0.35 or 4. The vertical direction at which one can see this maximum production either in terms of shear or buoyancy. What actually happens at that particular locations? Why it shifts all the way up?
Yeah, I think that's a good question. So the reason this is the mixing layer basically. So this is the thin. So if you look at it from a thin mixing layer point of view, so as the fluid is kind of moving, as the denser fluid is moving into the lighter fluid, then you have a zone of mixing, right? And this particular spike in all these production, buoyancy, and dissipation are actually capturing that mixing layer, the thin mixing layer that is present everywhere here. So, is it clear or?
Yeah, I understand. Basically, it's more like the amplitude of the disturbance or energetics spread all the way up, and that's also one of the reason this maximum value shifted all the way up.
Which maximum value? Sorry, I didn't.
For example, pick green, yeah.
So okay, so the maximum value is here. So this is starting from 0. So this is the bottom of the tank. This is the bottom layer of the tank. So near the bottom layer, there is not. I mean, of course, dissipation will be there because of the wall effects. That's why you're seeing something. But if you look at the production and buoyancy, they are almost 0. And they peak only in this mixed layer. The peaking occurs only within this small shear zone, if you may.
Correct. Right? And this peak value means basically the shift in peak value, shift in the vertical direction is because the zone is actually starts spreading all the way upwards.
Yeah, so there is only a zone shifting in the sense, yeah. So you are talking about if I draw a line.
Right, correct.
And then that is experimental uncertainty, I think. And I mean, that's because this is non-dimensionalized. So all of them should kind of peak at the same location.
Right.
But there are some inconsistencies in the peaking value because you have some, these could be measurement uncertainties as well.
I see. Right. Yeah, thanks a lot.
Right. So since I have done Z by H, it should peak at the same value, but there is very little shift. So I wouldn't kind of, I don't think it is dynamics related. It is more.
I see.
Okay.
But because can I just connect that?
Okay.
Yeah.
I'm just wondering, like, because the red zone and the blue zones, they are not equal amount. That can also be the reason in terms of dynamics. Like, I mean, do we begin with equal amount of lighter fluid?
No, we don't. So lighter fluid is much more than the heavier fluid. So the heavier fluid is only it's much smaller volume compared to the lighter fluid. But I don't think, because we have non-dimensionalization should take care of that, right? Because if we are only doing it in H in the vertical direction. So I'll try to think about it, but I don't think so.
Yeah. Thank you so much, sir. Bye. It's quite interesting.
Yeah, thank you.
So next, Tanmay, please unmute and ask.
Thank you, Professor Sridhar, for a very wonderful talk. My question is regarding how are we actually computing this buoyancy frequency? Because this is a case of a very transient flow, and at any particular cross section, the density profiles are all very different. So in terms of calculating, for example, buoyancy Reynolds number or the gradient Richardson number, we need this n. So can you tell a little bit about the processes that might be going on for that?
Yeah, absolutely. Yeah. That again, a very good question. So basically, what we are doing is, if you can see here, so it's a transient flow. So we are using a moving time average method. So what we are doing is we are taking one small window and we are advecting it along with the current after the front has passed away. Okay. So because of course, if we start from the front, then we are in trouble because we can't track the front after it has gone out of the integration window. So we only start, so like I said, we only look at the slumping phase. So which is let's say starts from the head of the current. And then we use a moving average window to get the average field. Okay. And of course, so the point is that we know that the slumping phase occurs, the slumping phase of this particular system would occur where would occur up to a point where the bulk velocity doesn't change. So we know the duration for which that occurs. So we are kind of calculating an averaged value of this n square in this entire window. If you understand what I mean. So it's not, of course, at every location n square is going to change. You are right. But if you kind of average it over the slumping phase, okay, I cannot define the slumping phase because this is just one instantaneous shot. We have to go to the movie probably, but let me try to do that. Yeah. So once the current, so you can see that the current is moving down. And once the front has passed, you can see that there is 20-25 seconds where your velocity. So we know the velocity, right? We know the velocity of this of the head and the body that are moving beyond, that are kind of following. So we look at the velocity, and then we say that okay, this 30 seconds is the window which we should average. Okay, and we do a moving average where we move at every time slice. And once we do that, we get a value at every location. So at every location and every time. So it's at one particular time and every location we get the value of your n square or your velocity u prime, v prime, and everything. And then we do.
There is a confusion for me as well.
Yeah.
So n involves d rho by dz, no? D rho mean by dz.
Right. D rho by.
So how do you get d rho? It's in the transition zone, or how do you get d rho by dz? Huh?
D rho by d. So if this is the thing, then we have a vertical cross section here, correct?
Right.
So we can draw a vertical cross section at every instance of time. So wherever your gradient is, wherever you have the gradient the rho, then you can get the n square because it's basically profile based.
So it's in the transition zone. Basically, that's where the d rho by dz you take into account.
Transition, I don't call it transition zone because it is confused. So it's a slumping phase. So slumping phase is a zone where things are quite quasi steady for quite a long period of time.
I see.
Yeah. So transition zone becomes difficult because it would have, so you assume that it is always changing. But in the slumping phase, your statistics are, at least mean statistics are quasi steady. That pretty much we have ensured that.
I see. Okay. So the light fluid and heavy fluid, and there is some kind of linear profile if you take a big enough region.
Yeah, absolutely. So I don't have, I had that, but I removed it because I thought it would be, so it's very similar to this, if you may. It's very, very similar to this profile that you see.
I see. Okay.
So there is a region where you can actually calculate the n square. So it's an interfacial n square that we calculate.
So I think that should answer Tanmay's question, right, Tanmay?
Yes, definitely, sir. Thanks very much. Really enjoyed reading the papers as well. They're wonderful.
Oh, thank you so much.
Great. Any other question?
Yeah, first of all, very nice talk again. Thanks a lot. Yeah, it's Ambrish here. So I just want to ask, I think you showed on one slide the eddy diffusivities, momentum as well as density. So yeah, I think the next after this, this one exactly. So the fluid is water, I assume.
Yeah, the fluid is water, correct.
Okay, okay. Miss, have you looked at the ratio of these two diffusivities? Roughly like like turbulent Schmidt number. What is the turbulent Schmidt number for this case? And is it saturating with an increasing Reynolds number to some value? I'm not sure if you have looked at this, but I was, yeah.
Yeah, we haven't looked at that. I mean,
okay.
Yeah, so the reason we did this is because there are some parameterizations that are reported in the literature.
Yeah, yeah.
We just wanted to see how well do they match if
okay.
Experimental parameterization that we get from our experiments.
Okay, okay.
So something we can do. I mean, I think that would be something we could look into.
Okay, and this is averaged over the region you are looking at, basically.
Right. This is time averaged as well as space averaged.
Space averaged, but space averaged over the window where you showed the movie, I think. Yeah.
Right. Right. Only in the slumping phase of the current. That's all. Okay.
It's nice to see that they are increasing, and they are. I assume that they are much more much bigger than the corresponding molecular diffusivities.
Oh yeah. So that's why we have. You can see that there is the denominator is it's
okay.
Kind of, normalized.
Yeah.
So this is 60. 60 times, 40 times more than your normal.
Okay. Yeah. Okay. Yeah. Good to see you. Thanks. Yeah.
We'll keep that in mind about the Schmidt number thing. It would be easy. I mean, I don't think it will be very difficult to calculate that and look at the comment that you mentioned. Thanks.
Yeah, actually, we recently looked at the turbulent Prandtl number behavior as a function of Prandtl number, basically, in thermal convection, of course. So here we found that for very low Prandtl number flows, like sometimes diffusivity or turbulent diffusivity is not much larger than the molecular diffusivities.
Oh, okay.
And the turbulent Prandtl number is like it's decreasing with increasing molecular Prandtl number, something like that. So I was having that in mind.
Okay.
But yeah, that's very nice talk. Thanks.
Thank you so much.
Any other question? Okay, Vamsi has a question. Vamsi, please go ahead.
Yeah. Hi, Sridhar.
Hi.
I have this question. So if you have this gravity current propagating at the top surface instead of the bottom surface, do you expect the dynamics to be very different, or I mean, at least qualitatively?
Okay, so you are saying like an interfacial gravity current. So some kind of.
Right, let's say a river plume at the surface. Yeah.
Yeah. So interesting question. I mean, I'm trying to think. I wouldn't think that the dynamics will be very different, because it will still behave as your because you will still have a mixed layer. I mean, you will still have a layer where the thin shear layer where a lot of your activity would be happening like this. Correct. So
right. Yeah.
At the first outset, I would assume that there will not be much difference because I'm looking at it only from the thin shear layer point of view, and it would not be very different. So
okay, would it be difficult to set it up experimentally?
Oh yeah, it is. It would be a little challenging because you may have to create different stratification zones, and people have done that. I mean, there are some groups. I don't know, from Hong Kong, I think, who have set up those interfacially moving gravity currents. The challenge is, the issue is that it may be easy to set it up and do bulk statistics, like just see what is the front speed, what is the instabilities and all those things. But how to probe the statistics would be very difficult. Like these finer scale statistics, it would be very difficult because you will have these 3 layers. So to match the refractive index of all the 3 layers and then do the dense velocity measurement may not be very difficult, but the density measurement becomes difficult when you have more than 2 fluids, because then refractive index matching and all goes for a toss.
Right.
Yeah. So bulk statistics, I would say it's not very difficult, but if you want to actually talk about these mixing efficiency and these turbulence fluxes, then it may be a challenge.
All right. Yeah. Thanks.
But I mean, I think maybe you are already doing setting it up numerically and trying to validate would be something which
right. We are doing that. So that's why I was wondering whether you are aware of any such experimental studies that they have done the
I only know of a couple of experimental studies where they have only measured the bulk statistics. I mean, the turbulence statistics, definitely not. I'm 100% sure about that.
Okay, all right.
Okay, so let me ask you several questions.
Yeah,
so sometime, okay, of course, we did not study this mixing in a shear, but we did some simulations of stably stratified flows in a periodic box. In fact, one student of mine is doing it right now. Abhishek Kumar did it before. So we varied. So for us, I mean, the 4 regimes you talked about, weak gravity, weak turbulence, strong gravity. So 4 combination, no, weak, strong, and two things. But we just took 2 parameters, Reynolds number and Richardson number. And we controlled by how much energy injecting. So we wanted a steady state profile. So our force was, I mean, we wanted to get to a steady turbulence, wasn't decaying. So we controlled these 2, Reynolds and Richardson. So we could get, I mean, of course, it's very easy to see high Reynolds and low Richardson, which will Kolmogorov spectrum. We are interested in the spectrum. Huh? That's what our main objective was. And then basically large Richardson and large Reynolds, but Richardson order 1. Well, sorry, Richardson order 1, and Reynolds was large. So that's Bolzino-Bukov scaling. Then Richardson more and Reynolds more, that will be stably, well, basically that becomes quasi 2D, and there are lots of issues with that, right? I think there are some still unsolved problems. So isn't it possible to just control these 2, Richardson and Richardson and Reynolds, and get to this 4? I mean, well, you have 3 regimes, but I think there should be 4 regimes, right?
Laminar is
well, 4th is trivial actually. Laminar and low Richardson, low Richardson and low Reynolds is laminar. Yeah, so that is kind of trivial, yes.
Right.
But so let's see. So one thing, strong stratification, strong turbulence. That is also important thing for
right. That is what is very difficult to. I mean, I think that's where a lot of problem is. Numerically, I think generating this is difficult. That's what we felt, because the DNS data from the previous, so only one. I mean, we could only find the DNS data from one of these studies. What we figured out was that the strong turbulence, strong stratification, strong turbulence regime is important, because I didn't go into the detail, because that will govern where. So in your mixing efficiency curves, what happens is with buoyancy Reynolds number, what happens is you start from a very low value, you come to a high value, then you get a plateau. Then after some time, since your dissipation becomes very high, you start again getting reduced mixing efficiency values. Okay, as REB increases, so your dissipation is increasing, so that's why you are again getting this drop. And this is known as the right flank. I mean, in this terminology, this is known as the right flank. So people are interested in where does this drop happen. So where does your mixing efficiency starts to drop again? That's also very important. So in weak stratification, strong turbulence regime, this will go up to some point, and then it will kind of drop down. But then in strong stratification, strong turbulence regime, the thing is that this keeps on going for a longer distance, because even though your stratification is strong, but your turbulence is also strong to sustain this mixing for a longer period of time. So this drop may not happen at so here REB is it's a log plot, so REB is at a value of 20. So this drop may not happen at 20, but it may happen at 100, 200, or maybe even 300. So that is what we are trying to understand. Okay, where so that's why universality is not a very clear picture, right? I mean, you have a lot of these issues where, okay, first thing is, what is the actual value of RIF star itself? What is the value of mixing efficiency itself? That's also that itself is a debate. And the second important thing is, where does this drop happen? Because you have to kind of change your parameterization to from this value to a different value in order to capture the the physics or the dynamics.
Okay, so I understand, but this 0.15, is there a way to get it from? Looks like, well, 0.12 to 0.2, but they are within a band. Is there a way to get it from analytically?
No, I don't think so. At least we haven't come across. So either experiments or some field studies or some kind of DNS data. So these are the only three ways. So as you can see, these are the only. So this is the experiment. Lozowatsky and Fernando did the field experiment, and they can see that value is everywhere. And
so in box turbulence, which we do it all the time.
Yeah.
The numbers, what we should look for, getting this efficiency. We don't really have shear, so we can compute these numbers. But maybe somebody would have done it. We've not looked at it, looked at the literature. But in a box turbulence, we have all sorts of things with us. What should we look for to quantify this this efficiency, mixing efficiency?
Yeah, so you will have to look. So like I think if you want to look at it, so dissipation, which is the viscous dissipation, and the change in the potential, the background potential.
And the steady state, they are all we have dissipation of buoyancy,
right? You will have.
And bottom is, well, it's under steady state. These are not changing with time. Huh? So, but let's say the top one could be dissipation of the potential energy.
Yes.
And bottom is the total dissipation. Is that correct?
That should be correct. Exactly. See. Exactly.
So we have those numbers actually. I mean, we can look at it.
Oh yeah,
I think we can also derive it maybe. I mean, for assuming kind of isotropy or. I'm not sure. I mean, that's.
I think the equation.
Of course, your flow is more anisotropic and more complicated, but you can do in a box where there's a gradient, d rho by dz. That's what you apply.
Right.
And we compute these numbers. I mean, Sadab, we have the numbers. You may have it for your study if you. Potential dissipation rate divided by total dissipation rate. You have a number?
Right. If you can,
he has the numbers. We can meet again and we can discuss this.
Yes, sure. I would be happy to exchange some value. I mean, we can check what values you are getting in the box turbulence.
Yes, actually, sir, from shell model we have this number, but for DNS we have run only two.
So what is for the shell model?
Actually, from weak stratification to moderate stratification, we have run the shell model simulations.
You have the numbers with you right now, or in your head, or no? Or in your, you can look at your draft.
Okay. Let me see.
Anyway, so he can get back. We can meet again. But we have those numbers from.
Yes, sir,
and I think. I mean, I believe we can have some handle on. Some handle analytically. I think that's what I think.
Okay, maybe I don't have any idea much about that, but yeah.
I see.
Probably
analytically, I don't mean analytically from starting, but there are models, I used to do renormation group stuff, compute the fluxes. So basically, we need to get these fluxes, the Kolmogorov fluxes. Right. So we can compute the flux of the potential energy and flux of the kinetic energy, and then we have both the numbers, right? You understand what I'm saying?
Absolutely right. That's exactly what you need. You're right.
Okay, great. So that's a good thing. Thanks.